Good morning, friends. Up to this we discuss about the radioactivity and also we discuss about the two type of the nuclear process. Nuclear fission process and nuclear fusion process. Right? Okay. Now generally the heavy nuclei, that means if the atomic number Z is more than 70 or the 30, so these nuclei are known as the heavy nuclei. These heavy nuclei are generally in unstable state. These nuclei try to attempt the stable state. For that process, they are emitting either the alpha, beta or the gamma decay and try to acquire the stable state. Right? Whatever the rate of decay or whatever the rate of emitting either the alpha, beta or the gamma rays. So that is known as the radioactivity. Or in other words, this heavy nuclei is how much active to emit the alpha, beta or the gamma. So that is known as the activity and that is called the radioactivity. Right? And last we also discussed about that, the characteristic of radioactivity. The radioactivity is the instantaneous and continuous. No any physical factor, the chemical factor or the parameter can affect the rate of disintegration or the rate of emission. We can't stop the emission of the alpha, beta or the gamma, or we can't change the rate of emission of alpha, beta and gamma. By keeping in mind this concept, we are going to discuss about the law of radioactive decay. How we can derive the mathematical relation of this radioactivity or the rate of radioactivity. Right? So the question is that write and derive the radioactive decay. Write and derive the law of radioactive decay. Now, in radioactive decay, that means the substance or the sample undergoes the alpha, beta or the gamma decay. The number of nuclei undergoing the decay per unit time is proportional to the total number of nuclei in the sample. That means in a heavy nuclei, the number of the atoms or the numbers of the nuclei are present. So this nuclei is undergoes by alpha, beta and gamma decay to obtain the stable state. For that purpose, they are emitting either alpha, beta or the gamma decay. The number of nuclei undergoing the decay per unit time is directly proportional to the total number of nuclei in the sample. That means the rate of disintegration or the rate of decay is directly proportional to the number of nuclei in the sample. So this statement is known as the law of radioactive decay. Again, the statement of the radioactive decay is that a radioactive sample undergoes alpha, beta and gamma decay. The number of nuclei undergoing the decay per unit time is proportional to the total number of the nuclei in the sample. Right? If n is the number of nuclei in a sample and delta n undergoes the decay in delta t time, therefore delta n upon delta t, that is known as the rate of decay, is directly proportional to the n. According to our statement. Our statement is that the number of nuclei undergoes the decay per unit time is proportional to the total number of nuclei in the sample. If n is the number of nuclei in the sample and delta n nuclei undergoes the decay in delta t time, therefore rate of decay or the rate of disintegration delta n upon delta t directly proportional to the n. To remove this proportionality sign, we introduce the constant, and this constant is minus lambda. For the delta n by delta t is equal to minus lambda n. Right? And this rate of decay, that is also known as the activity of a sample. Activity of a sample. By knowing the rate of disintegration or the rate of decay, we can know about how much this radioactive sample is active. Therefore, delta n upon delta t is also known as activity. I is equal to delta n upon delta t is equal to minus lambda n. Generally, we are using this equation of activity in numerical. Okay, now in this equation, delta n by delta t is equal to minus lambda n. Lambda is known as the decay constant or disintegration constant or the radioactive constant. Again, the lambda is known as the decay constant or disintegration constant or radioactive constant. Here, this negative sign indicates that as the time goes on, the numbers of the nuclei decreases in the sample. Because the more and more numbers are disintegrated, therefore the total number of undecayed nuclei in the sample is decreases, therefore this negative sign indicates. Again, the negative sign indicates that the number of nucleus decreases with time. Now, if the time interval is very small in this equation, by taking the delta t tends to 0, the rate of disintegration or the decay dn by dt is equal to limit delta t tends to 0, delta n upon delta t is equal to minus lambda n. Therefore, dn by dt is equal to minus lambda n. Clear? Now we are interested to obtain the equation of exponential law of radioactive disintegration for the radioactive decay. For that purpose, we assume that suppose at time t is equal to 0, the number of undisintegrated nuclei is n0 and at time t is n. Now from this equation, dn by dt is equal to minus lambda n, take the dt in this side and n in this side. Therefore, dn upon n is equal to minus lambda dt. Minus lambda dt. Now, indicating on both sides, because the left hand side is in terms of the number of nuclei, while the right hand side is in terms of the constant in time. We are taking the integration on left hand side with respect to the n, or in terms of n, while on right hand side we taking the integration with respect to time. Therefore, integration of dn by n is equal to minus integration of dt. Initially, we assume that at time t is equal to 0, the number of undisintegrated nuclei is n0, and at time t, the number of undisintegrated nuclei is n. Therefore, we are taking the finite integration between t is equal to 0 to t, while in terms of number of undisintegrated nuclei from n0 to n. Therefore, we take the limit n0 to n, integration dn by n is equal to minus lambda, integration t is equal to 0 to t. T is equal to 0 to of d. Now we know that the integration of 1 upon x into dx is equal to ln x. Is equal to ln x. So here the same formula, integration of 1 upon n into dn. So that is the ln n. Therefore, ln n in its value varies from initial value n0 to final value n. Is equal to minus lambda as it is. Now integration of dt. Integration of dt is equal to integration of t is to 0 into dt. That means the t is to 0 plus 1 upon 0 plus 1, right? So it's equal to only d. Therefore, Integration of dt is only t and its value varies from initial value t is equal to 0 to final value t. Again, here we take the integration on both sides, right? So integration of dn by n is equal to minus lambda is constant, taken out, integration of d. Now, the initial and final value of time n are given, t is equal to 0 to t. At that time t is equal to 0, the number of undecayed nuclei is n0, and at time t, the number of undisintegrated nuclei is n. Therefore, taking the integration of dn by n from n0 to n is equal to minus lambda integration of dt from t is equal to 0 to t. Integration of, according to this equation, 1 upon x dx is equal to ln x. So here, integration of 1 upon n into dn, ln n, value varies from initial n0 to final n, is equal to minus lambda as it is. Integration of dt is t, value varies from t is equal to 0 to t. Okay, first we substitute the final value, and from this the initial value is subtract. Therefore, ln n minus ln n0 is equal to minus lambda common, final value of t is t, initial is 0, that means the t minus 0. Therefore, ln n upon n0, according to the property of logarithm, subtraction of the log is the ratio. Therefore, ln n upon n0 is equal to minus lambda. Remove the ln, that means the taking the both sides base e. Therefore, n upon n0 is equal to, left hand side is in exponential form, e is to minus lambda t. Right? Therefore, n is equal to n0, e is to minus lambda t. Is the exponential law of radioactive decay. This equation is known as exponential law of radioactive decay. From this equation, we can also write down in terms of the activity of a sample, I is equal to I0 e is to minus lambda t. And also in terms of the mass of a substance at time t is suppose the m, and initial mass is m0. Therefore, m is equal to m0 e is to minus lambda t. So this term of the equation we are using in numerical. Right? So there is the most important theory question of this chapter, frequently asked for each and every year. Write or state the law of radioactivity and obtain the equation n is equal to n0 e is to minus lambda t. Or write and obtain the exponential law of radioactive decay for the radioactive disintegration. So n is equal to n0 e is to minus lambda t. Very easy, but here the integration is taken, and keep in mind the integration of dn by n is ln n, and integration of dt is only t. And then we need to substitute the value from initial and final value, and we obtain n is equal to n0 e is to minus lambda t. Clear? After the discussion of the radioactivity or the law of radioactivity or exponential law of radioactivity, we derive the n is equal to n0 e is to minus lambda t. That means the number of undecayed nuclei in a given sample is decreases with time. Right? Initially, the rate of decay, that means the rate of disintegration is more, because the rate of disintegration is directly proportional to the undecayed nuclei in a given sample. Initially, the undecayed nuclei in a sample is more, therefore the rate of disintegration is more. As the time passes, more and more nuclei are going to disintegrate. Therefore, the number of undisintegrated nuclei also decreases with time. Therefore, the rate of disintegration is also decreases with time. That means becomes the slower. Right? Okay. Now the next question is that do the graph of time versus the number of undecayed nuclei in a radioactive sample and write its characteristic. What is the graph of disintegration of the nuclei? For that purpose, we take the time on the x-axis and number of undecayed nuclei on y-axis. So initially time t is equal to 0. The maximum number of undecayed nuclei in a given sample, that is the n0. As the time increases, so more and more nuclei are disintegrated. Therefore, the number of undisintegrated nuclei decreases with time as shown in the graph. And this graph is known as the decay curve. There is not a straight line. There is the decay, exponentially decay takes place, or the exponentially decrease in number of undecayed nuclei in a given radioactive sample. Now the characteristic of this graph is, first, the number of undecayed nuclei in the radioactive sample decreases exponentially with time. The number of undecayed nuclei in a given sample decreases with time exponentially. Right? Not the directly proportional to the time. Because the n is equal to n0, t is 2 minus lambda t. That is the exponential form. That is the exponential form. Okay. Now, in the beginning, the disintegration occurs quickly, and as the time goes on, the disintegration becomes the slow. Here, initially, in initial time, the more number of nuclei are going to disintegrate. As the time increases, therefore, the rate of disintegration is decreases. Because the rate of disintegration, dN by dt, is directly proportional to the undisintegrated nuclei at that time. So as the time increases, the number of undisintegrated nuclei is going to decrease. Therefore, the rate of disintegration is initially quickly, and then as the time goes on, the rate of disintegration becomes the slow. And this graph is also known as the decay curve. Now the second characteristic, from the graph, one can determine the rate of disintegration and also the half-life time. Now, from this graph, one can find out the rate of disintegration, that means the dN by dt. As we take this time interval. So whatever the decrease in number of undisintegrated nuclei, that is our delta n. Delta n upon delta t, that gives the rate of disintegration. That gives the rate of disintegration. And half-life. Half-life is the time for which the number of undisintegrated nuclei becomes the half of the initial. The time interval for which the number of undisintegrated nuclei becomes the half of the initial, such time interval is known as the half-life. So initially, the number of undecayed nuclei are n0. Now here there is the n0 by 2. For n0 by 2, whatever the time is taken, that is known as the half-life of a given radioactive sample. Right? So from the decay curve, one can find out the rate of disintegration and also the half-life of a given sample. Third is, if the decay constant lambda is large, the rate of disintegration is also large. So from this equation, dN by dt is proportional to n, therefore dN by dt is equal to minus lambda n. Lambda is known as the decay constant or the radioactive constant. If the value of lambda for a given sample is large, here the lambda is not constant, that is depends on the type of radioactive sample. For different radioactive sample, the value of lambda is also different. Some radioactive substances are disintegrated in very small time interval. For this type of the sample, the value of disintegration rate, that means the decay constant is large. Right? If the decay constant lambda is large, then the rate of disintegration is also large. And next is, regardless of the type of the radioactive substance, it takes the entire decay for infinite time. No any radioactive sample is, after some interval of time, it is not possible, the rate of the emission of alpha, beta or the gamma is stopped. For long time, that means the infinite time, that is decaying by radiating the some energy. Initially, when the substance is very active, at that time the alpha particles are emitted. After that, as the activity decreases, then it emits the beta particle, either the electron or the positon. And after that, it emits the energy in form of gamma rays. So, for a long time, that means the infinite time, the rate of disintegration is continuous, not stop. Right? So, first the law of graph of the number of undecayed nuclei versus the time. And this graph is known as the decay curve. Right? So, what are the characteristics of this decay curve? First is the number of undecayed nuclei in a radioactive sample decreases exponentially with time. Already we know that n is equal to n0 is to minus lambda t. Note the number of undecayed nuclei decreases directly proportional to the time. It exponentially decreases with time. Now, in the beginning, the disintegration occurs quickly because initially the number of undisintegrated nuclei are more, and as the time goes on, the disintegration becomes the slow. This graph is also known as the decay curve. From the graph, one can find out the rate of decay, or the rate of disintegration, and also the half-life of a given radioactive sample. Third characteristic is that if the value of the decay constant lambda or the radioactive constant lambda is large, then the rate of disintegration is also large for a given sample. And now fourth characteristic is that regardless of the type of radioactive substance, it takes the entire decay for the infinite time. So that is depends on the radioactive sample. The activity is never becomes the zero. Right? Activity is decreases with time, but never becomes the zero. For infinite time, the sample is active. Okay. After that, the next question, explain the decay constant and define it. What is the definition of decay constant lambda? Already we derived the equation of the rate of decay for the activity loop, for the law of radioactivity. According to the law of radioactivity or rate of decay, dN by dt is equal to minus lambda n. That means the rate of disintegration of the nuclei is directly proportional to the undecayed nuclei at that time in that sample, where the dN is number of decayed nuclei in delta t time. What is the dN? dN is this. Number of nuclei decayed in delta t time. And n is the numbers of undecayed nuclei at this time in a sample, or at time t. And lambda is known as the radioactive constant or the decay constant. Again, from law of radioactivity, dN by dt is equal to minus lambda n. dN is number of decayed nuclei in delta t time. N is the numbers of undecayed nuclei at time t. And lambda is radioactive constant or the decay constant. Right? From this equation, lambda is equal to dN minus dN by dt upon n. Lambda is equal to minus dN by dt upon n. From this equation, we define the decay constant. First, what is the SI unit? SI unit is second inverse, day inverse, or the year inverse. Because the decay constant is inverse of the time. Therefore, its unit is second inverse, day inverse, or year inverse. The ratio of rate of disintegration for a given instant and number of undecayed nuclei at this time is known as the decay constant. Again, the ratio of rate of disintegration, right? Rate of disintegration for a given instant to the number of undecayed nuclei at this time is known as the decay constant or the radioactive constant. Again, this equation, the definition of decay constant, dN by dt, is the rate of disintegration for a given instant, and N is the number of undecayed nuclei at that instant. This ratio is known as the decay constant. The ratio of rate of disintegration for a given instant to the number of undecayed nuclei at that time is called the decay constant lambda or the radioactive constant. Now, mathematically, expression of this equation, the probability of disintegration per unit time of a radioactive element is known as the decay constant. Here dt is 1, therefore lambda is equal to minus dN upon A. That represents the probability of disintegration of the nuclei. Therefore, the mathematical definition of decay constant is that the probability of disintegration per unit time of a radioactive element is known as decay constant. Clear?